So our final lecture of the afternoon is the James Dungey lecture. I shall read out the citation for this one, but Sandra can come and prepare herself, I think. So, Professor Sandra Chapman has made outstanding contributions to our understanding of the solar wind and the magnetosphere. Among her many achievements, she has led landmark research on turbulence in the solar wind and nonlinear dynamics in the magnetotail. Her research career is strongly interdisciplinary, spanning space and laboratory plasma physics, climate and neuroscience. She contributed to the data analysis and modelling of turbulence both in space and magnetically confined fusion plasmas, as well as focusing on wave-particle interactions, plasma acceleration and heating. She has demonstrated a strong commitment to engaging with the general public, most recently through a project exploring how scientific ideas can be communicated through art. She is an outstanding speaker, as I'm sure we'll find out in a few minutes, who can draw on the application of nonlinear and complex systems concepts to a wide variety of fields, even outside physics. For these reasons, Professor Chapman is awarded the Royal Astronomical Society's James Dungey Lectureship.
That's it? Yeah. Okay. I'll start, sorry. Gosh, well, no pressure then. Thank you for that wonderful introduction. And indeed, I work on a lot of things, and the names I put up here are just a few people who work with me on solar wind, because I'll talk a little bit about that. But of course, really what I want to talk about is Jim Dungey, so if I can make this work. Yeah, okay. So I want to talk about the title of this, was Thinking in Pictures. And it's very apposite for Jim's work, because I want to talk about some of his main ideas which come from thinking in pictures, but I also want to talk about the power of thinking in pictures, that how we do physics this way, and how we're still kind of doing this, because it's a really great shortcut for problems which are in fact rather hard, and of course reconnection is one of these problems, turbulence is another. Okay, so that's kind of what I want to talk about. And I'm really pleased that the RAS gave me this chance to talk about Jim, because I was a student at Imperial, and he was still the head of group when I was a student there, and I was Stan Cowley's student. Stan Cowley was Jim's student, and so he used to call me his grand student, okay? And so he was a lovely person to know, but very challenging as well. He would always ask you questions, and I still have letters in my cupboard of problems he'd sent me, which I haven't answered. And this was kind of Jim's style, okay? But Jim's real thing was to... Thank you. Put some water in, that would be fantastic. Thank you. Was Jim's main idea, and it's captured here. This is a great picture of Jim. When he retired, his students gave him this gift, and it's a weather vane, and you can see it's the open magnetosphere, which is what I'm going to talk about. Okay, so there's the Earth, and that's the sunward side, and there's the tail, I think. Okay, and that's Jim holding this aloft. And I found some wonderful quotes of Jim talking about this. He's thinking about topology. In particular, he describes when he first had this idea, and he was relaxed. He was preparing a talk, I think. He was sitting out on a nice terrace, okay, Paris, somewhere like that. And he was talking about this, how he got this picture. And he's saying, you know, he basically saw the idea. He thought in pictures, because at the time people didn't have a picture of the open magnetosphere. And he talks about it. He says, you know, I saw the picture, or at least thought I did, in 3 dimensions, where the electric field over the polar cap fitted in with a reconnection picture. So you know about reconnection, and for those who haven't seen it, I'll show you a picture of reconnection in a minute. And you put that together with the dynamics of the magnetosphere and come up with a picture. But it's really a 3-dimensional picture, and it moves as well. So it's really a movie that you do in your head. And then he went on to describe the details of how this describes polar cap convection and so forth. And so it was a picture. Now, maybe to think, I mean, when I was a student at Imperial, when I turned up, I was given a desk and there was no computer on it, okay? Because there weren't any. If you wanted a computer, you had to go to the computer room where there was a terminal, you know, and if you wanted to make a picture, you had to go to the special Tektronix terminal, okay, and make a picture on there. And if you wanted a hard copy, you had to order it and go and get to the computer centre and wait. And so people were really used to, I mean, I grew up with having to have the skill of holding pictures in your head of physics. You know, I mean, the older people here will know what I'm talking about. This is what you had to do. The younger people won't. They could just do it on the computer now. But I think this is kind of important. And it's a kind of question that maybe to leave you with is, you know, are we still keeping this skill? Because now everything is so easy to do. I'm going to show you some lovely movies, and we're so used to seeing these visual things. Because Jim had this skill, okay. And at the time, of course, there is this skill of thinking in pictures, but then people ask, well, where's the physics? And at the time, people kind of said, well, this is great, you know, but they didn't believe it. They thought it was artistic or something, this lovely picture, when he showed it to them. Okay. Because the question is, well, there is physics in it, and that's what I want to talk about. So this is his picture, okay. It's very simple. So here is the idea. Here is the Earth, and the plasma is flowing in from the sun over here, and here is a magnetic field. And then you have reconnection, and the idea is, well, you have reconnection here, you can have a reconnection in the tail, and so particles and magnetic flux can convex over the top, and it can go around. So in it comes, convex over the top, and comes around the sides, so out of the plane. But there are rules. I mean, the reason this picture works, there are physics rules in the picture, and this is the thing I want to kind of get over. And what are these rules? Well, you can't destroy magnetic flux. Okay, so magnetic flux is conserved, and out in space where your length scales are long enough, the magnetic field is frozen in and it's carried along with the plasma. And so you can't get rid of it. So if you draw a line here or a line here, the only way you can change the lines is to do reconnection. And you do that by doing some other kind of physics on a small scale. So this is E plus V cross B equals 0. So this is the second rule. If you have a V and a B, a velocity and a magnetic field, you generate an electric field, and then, okay, you map that down somewhere onto the ionosphere where there are collisions, and then you can have currents. And so this picture here is the flow pattern that you see on the ionosphere. So all this comes out from just obeying these simple rules. I can't get rid of magnetic flux. I can't have, div B non-zero. And I can only break the field lines where there's reconnection. Very simple idea, but it's a solution to fully nonlinear equations on multiple scales. There are physics coupling on multiple scales. And it works because you're kind of using the conservation rules are the rules that must also be obeyed by the complicated set of nonlinear equations that I'm not going to write down. Maxwell's equations and magnetohydrodynamics have those rules built into them. So really what you're doing is you're saying, well, if I keep the symmetries that are in those complicated nonlinear equations, if I hang on to the symmetries and the conservation properties, and I make a picture that uses those, then the picture will be correct physically. And that's the power of this idea. And it's predictive. Here's one prediction that came out from Jim's idea. This is a paper in JGL. This is the whole paper, by the way. I think this is great. We don't get to write these anymore. But what he's basically saying is, well, if I take my little picture, I can work out how long the tail is, because, of course, I know how fast the solar wind is going, so I know how long it takes this field line to convect over the top and come back into the tail again, so I know how long the tail must be. So the physics, the drawing is a predictive thing, and that's kind of a clue that there is really physics built into it. So the second thing we want is we would like to organise our observations. There's this kind of idea that you observe things and it's all nicely organised, but certainly in space physics this is not the case, because what you actually have is a lot of data coming from satellites that are going round and round. Here are some pictures that people have drawn. You have the Earth here, so satellites, some will be in the plane, some will going out of the plane, and what they do is they measure magnetic field and they measure plasma density. And they measure boundaries in particular. You can see when you cross boundaries from one kind of plasma to another. So you have many crossings of different boundaries. And you kind of have to join the dots up. So you need a kind of picture to do that. So Jim's picture kind of organises all of the observations, many, many observations that you have in a dynamical kind of way. So there are these two jobs that the picture is doing. Okay, so the kind of art thing. What's going on here? We're drawing pictures. It's literally just drawing a picture. Okay, and so there are various appealing things. Well, one is it simplifies. I mean, the simplest picture may not be the true one, but we tend to go for that. Okay, this is Occam's razor. It's a simple. We have a lot of complicated observations. This picture organises them and makes them simple. And it's elegant. But what do we really mean by elegance? I'm interested in art, obviously, you've heard about this. When something is elegant, really it means it follows a pattern, it has some symmetry. And the thing that's beautiful in physics, when you look at something, you think, that's really kind of nice. It is that you're appreciating the symmetries of that the beauty of an equation. That's kind of what it is. And that's, to me, the beauty of it. The truth of it is things like this. Well, you'd want it to be predictive, obviously. There's a question, well, is this universal? Does the system always do that? Because if the system always do that, you'll see it all the time. Okay, so universality, so you see it all the time in nature. And that it captures the relevant properties of the physical laws. Okay, the things that are underneath the equations that we can't solve. Okay, so successful pictures actually solve equations that we are not able to properly solve, or we can only partly solve, because they just have couple across so many length and time scales, and because they're strongly non-linear. And it gives you a solution. I mean, that's what Jim did. Okay, they capture the observed by stylized facts. I mean this idea that you have lots and lots of data, doing lots of different things, and it organizes it in a successful way. And they make testable predictions. So this is the idea of pictures, the kind of what Jim was doing. But why pictures can be so powerful if they're done in the right way, that they capture physics. Okay, so I'm going to ask the chap upstairs there if you just click on this a few times. This is a simple picture of reconnection. So basically, the flow is coming in bottom and top. These are magnetic field lines. They've been coloured in. And so you can see they join in the middle, and then off they go. Okay, so this is a picture. Okay, you can stop doing it now, so thank you. So we're going to go, that's why I didn't put it on continuous loop, you kind of go mad. So this is what's happening in here. This is a nice, simple picture of it. So this is lovely, but as was Jim's style, this is a kind of exercise or two left to the student here, because two that I kind of want to allude to is, one is what is actually happening in this region, and the other is how does the plasma then gain heat, because what's happening is flow is coming in, flow is going out. So really what you're doing, these field lines will eventually kind of straighten out. So they're giving their magnetic energy to the plasma. Okay, but this plasma is pretty much collisionless. So, how does it increase its entropy then? How does it heat? Okay, and this is a kind of little exercise for the student left by Jim, how this all works. So I will talk a little bit about that, and how this kind of maps into some more recent things. Okay, so this is the basic idea of nice 2D reconnection. And this is what happens if you do a simulation. This is a fairly recent one, and it's called PIC code. Okay, what does that mean? It means we're trying to resolve down to the finest scales of the plasma dynamics. So plasmas, you can think about them as being fluids on the large enough scale. But of course, plasmas are also made up of charged particles. Okay. And so what this code is doing is following all the charged particles and the full electromagnetic fields. And so when you do a reconnection simulation, you try and put this in a box. So here is the box. So it's this direction is this direction, okay? And the reversing direction is this direction. And this direction is the kind of in the board part, okay, the third direction. And there's a guide field sticking out in the third direction in this simulation. And you can see it's a mess, okay? This is being shown things like currents and so forth. Absolute mess. What's happening, rather than these nice field lines just coming in, of course they can reconnect all over the place in 3 dimensions, and they can interact with each other. Turn that, sit for something. Let me take that in. So, the interesting question here is then, is the kind of roughness of this system, these interactions, is this now important? And that's kind of what I want to talk about. And that's this kind of idea that the turbulence is having a role here. So is it the reconnection generates turbulence, or that the turbulence is important for the reconnection, or does it just happen to just come along for the ride, or what? Okay. So my main interest is turbulence, and so that's why I'll talk a little bit about that. Okay. So in order to understand turbulence, I'm going to need to make some pictures for turbulence as well. But these are physical pictures. Okay, so here's a lovely picture of turbulence. Leonardo da Vinci, of course, and he pretty much gets all the physics in there, in this nice picture. Because if you look at it, okay, there's on the largest scale, there's a flow, okay, which is driving the turbulence. Okay, now in reconnection we have an outflow, Okay, the reconnection drives the plasma out. So that could just drive turbulence anyway, and the turbulence could then heat the plasma somehow. Okay, so that in itself is interesting. But if you look at all these lovely little swirly things, you can see in the turbulence inside here, they all kind of look the same, but some are bigger than others. They kind of are the same thing, but shrunk down or bigger. You know, small scales, a scaled down version of big guys, okay? And that's kind of the character of turbulence, that it looks the same on different scales. And how it does that in detail tells us a lot about the turbulence. What else do we see? On the very smallest scales, you can see there are little bubbles, because there's a crossover to a different kind of physics here. On these larger scales, it's being a nice fluid. But if you go small enough, it can't just be a fluid anymore. So there are lots of bubbles in the fluid here. So on these smallest scales, maybe there is some physics that could turn the fluid motion of the plasma, the turbulent motion, into heat. And in the plasma, the smaller scales are these kinetic scales where the particles themselves are important. And the larger scales, you have a magnetofluid. Okay, so we've got all these different kind of aspects of turbulence in reconnection that I want to talk about. Okay. So what I want to do is talk a bit about turbulence, and I want to give, I know it's a very broad audience, so I want to kind of give an overview flavour and try and use this power of pictures to get the idea over quite quickly, even if you've never really thought about it before, but just the essential idea. But I also want to give some detail for the experts, because they'll be getting bored, okay? So it's quite a tough job, but I'm going to try and do both these things at once, and I'm going to use this thinking in pictures idea. Okay, so picture of turbulence now, but again, it's a picture with some physics in it. So this is Richardson's picture. And so remember, you've got all these eddies on different scales, and so the idea is that you drive the thing on the largest scale, like the flow in Leonardo's picture, and the eddies all kind of break up, okay? But they do it in a self-similar way, that this one breaks up into two guys, and that one breaks up into two guys and two guys, and the size of that one is some fraction of this, and the size of that one is some fraction of this. It's a kind of self-similar scaling kind of pattern. And so when you try and measure turbulence or tell if something is turbulent in nature, you're looking for this property of self-similarity or scaling, okay? And so I wanted to just talk about what this means. It's a very simple idea. If you look at a tree, if you try and make a tree on a computer, this is how you'd go about it. You'd say, okay, I want a rule for the tree. So I'll have a big branch, and each branch will make 3 smaller branches. And each one of those will make 3 smaller branches. It could be slightly random. It could be 3 or maybe 4 sometimes, roughly 3 on average. Okay. But this kind of would look like a tree if I did this. Now, how can I tell what kind of tree it is? You go out and measure the tree. So we're going to count the branches. And I'm going to make a little plot of the length of the branch and then the number of branches of that length. There are lots of small branches and just a few big ones. Okay, but of course there's only one big guy, and there are 3 on the next guy, and then there are 3 times 3, so there are 9 on the next guy. So you can see this is going to be a power law. So really, when you start looking for scaling in anything, trees, turbulence, whatever, you're looking for power laws, and you're getting something out of the data and making a plot like this, and then you go plot it log and look for a straight line, and then you try and measure the slope of the straight line, because the slope of the straight line is telling you what the rule is, that each one gives me 3 and it's a fifth as long, 3, 5. So this number is telling you what the exponent for the tree is. So you're going to hear me saying exponent, exponent, exponent all the time. This is what I'm trying to measure, and different exponents tell you different about what the tree is going to look like. Here's an example, sort of topical one. These are obviously Christmas trees. Well, they're not real, they're green plastic things. They have lights on. How do I know they're a Christmas tree? Well, they've got a certain shape to them, and the small guy looks like the big one scaled down. Okay, so there's an exponent for these trees. These are clearly not, these are just so wrong. These are not Christmas trees. I mean, they've sold as Christmas trees in the US, okay. But they're different. You can see they're still green and they've still got lights on them, but the exponent is different. They're not the same kind of tree. So different kinds of exponents, different kinds of tree, and so different kinds of turbulence. And that's what we're going to try and measure, okay? Okay, so, and it means some physics. I mean, this business of the exponents, and I'm going to try and explain what that is again by talking about Richardson. Okay, so the idea is that each one of these eddies contains some energy because it's a swirling motion in the flow. It's got a velocity. So it's got an energy which is like v squared, okay, kinetic energy on that scale. So when one of these guys breaks up, it gives its energy to the smaller guys. So there's a rate of energy going down from one scale to the next. So if I want to know this rate, I say, okay, well, what's the energy in this guy? It's dv squared. That's the fluctuation in velocity due to this guy. And how long does it take? Well, that's the time. And that gives me an energy transfer rate, okay? And time is just distance over velocity. R is the size of the thing. Okay, so the energy transfer rate goes like dv cubed over r. Okay, and then, so there's some kind of rule. This is all of turbulence really captured here, so it looks a bit complicated, but worth giving it a go. But, you know, everything, dv to the m, all the moments of this go like length scale to the m over 3 times this guy. And this is the energy transfer rate. So they all go like r to the something. And this is the exponent that we're going to try and measure. So this is like the tree exponent, okay? So this is just telling you, it captures this idea that this guy and the way it breaks up into the smaller guys looks the same. So this process looks the same as this one and looks the same as this one. That's what we're capturing here, buried in this little exponent here. And this all depends on this guy here, which is the energy transfer rate. So this is the rate at which plasma energy is being pumped in and will eventually heat. So this is the heating rate, which we're interested in. Okay, and so there's two options that I'm going to talk about. One is that this energy transfer rate doesn't care what scale it's on. It doesn't know about scale. Okay, and so if I just say it's got some average value, then I just get this factor 3 in because it was dv cubed, because it was dv squared kinetic energy per length scale, okay, so dv cubed. So this thing just goes linearly. If, on the other hand, this guy does depend on scale, it's still going to do it in a scaling kind of a way. So then I've got to plug something, let's say it goes like r to the something. Then I get some exponents here which depend on the moment, on the number that I put in here. Is it dv squared, dv cubed, or whatever? And what I've drawn here is making, on a computer, spatial fields obeying these rules, okay? People actually do this when they make video games and films. This is how you do it. You use these things because they look like mountains. There's a reason for that, okay? But you can see the scenery looks different in these two cases. This guy, this looks like a very rough mountain, okay? The exponent, the number that I need, is the same everywhere. I need one number, the same roughness. This number is capturing roughness. Here, I need more than one number, and what it's telling me is that this exponent is local. So this is more like if you look out of your plane window, you see spiky mountains and then you kind of see a smooth bit. Spiky mountains are rolly plains, okay? So the difference between these two, you remember how rough it is this is the energy transfer rate locally. Here, it's kind of more uniform. I'm not saying it's not bursty, it's very bursty, but it's the same kind of burstiness. Whereas here you get a big burst and then nothing. So how this is working in terms of energy transfer rates is very different. So this number is the tree, these are like the different kinds of tree, okay, and my different kinds of turbulence. And so I'm going to go and measure them and use this as my way of measuring turbulence in reconnection. So if you're new to this and that's quite hard, it's hard. It's not you, I know it's late. It's tricky, no it is. Okay, so now we want to measure it. We want to measure these little fluctuations. And all we've got is a time series mostly, because you stick a satellite out in the solar wind or something and wait for the plasma to run by and you see stuff. Okay, and so what I do in this stuff, this is actually a simulation of some turbulence. It looks like kind of crumpled up fabric. Okay, and I want to measure on different length scales the fluctuation, the dv squared of my turbulence. Okay. And I don't have length scales, I have time. So I'm going to start talking about time. But really, the thing to think about is I have a ruler, and I'm holding it up to the flow and asking, what's the eddy like on that length scale? How big it is, and how can I compare it to a smaller ruler? So everything is about rulers. And so the way you get this out of data is you've got some time series, you bandpass filter it. So you take a bandpass filter and ask on a particular frequency band, and that's measuring my different eddy. I mean, there's different versions of this, okay, but that's basically what you're doing. And then we can go and calculate these exponents. So the deal is you get your eddy, your little fluctuations on some scale. You look at all the moments, and that tells me the exponent. So I make some kind of log plot to get these things out. And then I'm going to say, well, is that a straight line or not, okay? And that tells you what kind of things I'm seeing in terms of turbulence. Okay, you can press that other one. Hello. Yeah, it's just because it's nice. So this is just nice pictures of the solar wind, okay, this one in particular. This is the inner solar wind. And you can see the solar wind is blowing in a very non-smooth fashion. It's blowing quite fast, and it's fast enough to drive turbulence. And so people like me think it's a great turbulence laboratory. It's actually quite a horrible turbulence laboratory. You have to go and look for nice bits. Okay, but you have a satellite sitting in the solar wind, and you measure turbulence. Okay, and the clue, I mean, obviously there's been a lot of debate about, well, is it really turbulence, and what kind of turbulence is it? Okay, well, the first kind of clue is if you just look at the power spectrum, and that's what these plots are showing. So this is just in time, this is just the power spectral density of a component of the magnetic field, essentially, from a satellite. And you can see you have ranges where you get power law behaviour. So you think it was Kolmogorov-like or whatever. It's this idea that you have eddies breaking up and fluctuations on many different scales, and they're self-similar. So when I look at the power spectrum, I see a power law. Classically, what you'd expect to see in turbulence. So people expect this turbulence. This picture here is on MHD scales, on fluid scales. But the surprising and interesting recent thing is when you go on much finer scales where you start to resolve the particle dynamics on kinetic scales, you still see a kind of power law. It's a different one. And this is where it gets rather interesting, because we want to go and look at reconnection and say, okay, you know, we now can look on these two scales and see what's happening. So there's a whole world of interesting things in here that I don't have too much time to talk about. But at least there is some nice evidence that there is some turbulence in this lab, and we can measure things from it. Okay, so this is what doing that looks like. Remember that the tree, we have to go and measure a power law and then figure out the exponents, and there were two options. One of which is that it looked like the rough mountains and it was fractal, and the other is that you had the pointy mountains and the smooth plains. And those were the two options. And when you go look in the solar wind, you find both of these things. Interestingly, the multifractal guy you find on fluid scales. And this is kind of expected. People are kind of okay about that because that's what you expect to see in fluids. Okay, I work on fluids. To cut a long story short, this is the kind of thing you see. You see very intermittent bursts and then nothing. So, okay, MHD does a similar thing, and that's kind of nice. But when you come down these very small scales, on the kinetic scales, the scales of the particles, you're still seeing some turbulence, but it's different. It's more like the fractal guy. So it's not doing what a fluid would do. Now, maybe that's not surprising because it's not a fluid, but it's still doing turbulence. So this is a kind of open question as to what kind of physics this is involving, and you know, we argue about it, okay? But it's an interesting kind of signature, just put in its own right. This is kind of what turbulence does. But now we can go and look at reconnection and say, well, you know, we can use this as a kind of benchmark to see, is that what we're seeing in reconnection then, in these messy simulations, and in reality, okay? So to do this, here's the nice picture again. Yeah, if you don't, that's fine. So I don't know, I kind of go a bit psychotic after a while. So we're going to go and find reconnection in nature now, with a satellite or two, maybe 4 if you're lucky with cluster. How do you do that? The satellite kind of flies through here. Or maybe it's flying through, but the reconnection is moving around. It doesn't just sit there for you nicely, okay? So the kind of picture is like this, that you kind of fly through and you go from outside to inside. When you're inside, you see the exhaust. When you go through, you see the field changing, okay? And so again, we're using a picture to order the data. Okay, we're all quite happy with this, but it's got physics in it. You can't have any old change in the field or the flow. They have to obey basic laws of conservation, and that's what you do, okay? So we'd look for this kind of signature, and people actually spend their lives looking for these things. And here is one, okay? So somebody, not me, went and looked for this. This is an example of reconnection in the magnetotail from a satellite, okay? And it looks a horrible mess, unless you're kind of used to staring at these things and looking at them. But it has kind of promising features like in this middle region, you can see the flow going crazy, and you can see the field changes as you'd hope it would change. And the other really nice thing, we can see some nice heating, okay? And very spiky current. Now the current, we're getting this from 4 spacecraft. This is a whole extra tricky thing. How do you measure current in space? Well, you can't. What you have to do is you take 4 spacecraft and you measure the magnetic field, And then you say, well, Maxwell's equations, and I'll just work out from those 4 points what I think the current might be. Okay, and that's what's gone on here. And you can see it's very spiky. So this is very suggestive that there may be some turbulence in here, and it's, you know, doing some nice plasma heating for us, you know, and that's something to do with this reconnection site. So we kind of want to untangle all this, and that's the kind of interesting and tricky thing. Okay, so first of all, just looking at the spiky current, here it is again. What I'm just doing here is you take a threshold, okay? So you take a threshold and you ask how much energy dissipation, how much J dot E am I getting from the data outside the threshold, okay? And that's what this plot is. This is changing the threshold of J, and this guy is the heating. And so you can see for very low values, when you're kind of in the middle there, the average heating doesn't change at all because it doesn't care, you know, that there's no real spikiness. But as you get to large values, you're just seeing the spikes. You're seeing the average heating rate going up because it's all just happening in these little spikes. So these little spikes in J are really doing the job for you. These little plots here are for those who like statistics, the probability density, and it's non-Gaussian, okay? So they're very likely to get big guys, big spikes, much more than you would just from boring old Gaussian statistics. So this J is kind of interesting. It could be doing some nice heating from us that may have something to do with turbulence. Okay, so we want to know, well, is it like the turbulence in the solar wind then? Is it what you expect? And that's what I'm doing here. So remember with the trees, you're taking your ruler and you're measuring the lengths of things, and you're drawing a log plot and making a measurement, and you're measuring an exponent, and then you plot the exponent and you say, okay, is it like the mountains or does it have the rolling plains in it? And that's what this slide's about, okay? But the key thing is that you find on the fluid scales that it looks just like the solar wind. It's a nice fluid turbulence. And when you go down onto the scales where things are kinetic, it again looks like what we saw in the solar wind. So in these exhaust regions, you're seeing turbulence the same as you would see in the solar wind when we went and looked for it and everything was nice and easier to do. And so this is a kind of nice first thing, because otherwise you're just looking at these spiky things and you don't know whether this is fully blown turbulence or is it just a few spikes. And if it's turbulence, then maybe you could start looking for models of turbulence that tell you about heating and tell you, rates of things. So it's only a first step, but it's a kind of nice kind of physical benchmark to put numbers on the picture. Okay. So that was looking in real data. Okay, now I'm going to go and have a quick glimpse. I showed you this messy simulation, so I want to kind of analyse it, and I'll just give you a little highlight, really. Okay, so I'm going to go and do the same trick. I have to do a little bit of extra work because it's in a box, but that's not too bad. Okay, so here's back to this guy. So now I want to go to the simulation. Is it the same as what we saw in the magnetotail? Is it the same as what we saw in the solar wind, or what is it? Okay, so we do the same idea. I'm going to say, okay, I've got this mess, and I'm going to hold a ruler up. I'm going to draw lines in here and look on different length scales, okay, and look at the fluctuations and draw my straight lines. So first of all, these are just the power spectra, and it's horribly short range now because, and this is a real problem. I mean, it's a problem for real reconnection, but for simulations as well. You haven't got much tree to go on, okay? If you're trying to do this with a tree, you'd like to have lots and lots and lots of branches, but here you've only got a short region in space, so you can only make so much, so many different measurements with my ruler. So when you look at the power spectrum, you kind of see something like this. Maybe there's a straight line in there. This is a log plot of the fluctuations of the magnetic field, okay? We want to check it's not noise, that's what this is. I mean, simulations are very noisy. Okay, so I looked outside. Okay, so we do this trick of saying, okay, we want to measure the exponents again. There is just a little extra twist, and as I say, you're in a box now in the turbulence. Okay, and so when you try and plot the thing that should be a straight line, which is the moment of my fluctuation against length scale, it just looks horrible because you're seeing the box. But if you can do it for different moments, you can divide one by another, which is what's going on here, and divide out the box and get back to the turbulence. And that's what ESS is called. And that's what's going on here. So we see some nice straight lines and we can kind of measure these things. But this is a problem with pretty much all simulations, even ones where it's just turbulence, never mind reconnection in the box, that you've got a box and it messes up everything you're trying to do. So you'd use this trick to try and get rid of it. So we go and measure these things. We now get ratios of exponents, but that's okay. We can still say something. Okay, and that's what this little plot's showing. So it's basically asking this same question. Is it like the fluid flow? Is it multifractal? Or is it like the thing we saw on kinetic scales? And it turns out for the simulation, it looks like the fluid flow. So this is kind of weird, okay? So it does not, you know, you may have been thinking, oh, she's going to say it's all great, it all agrees, and we're all happy and we understand everything. Well, no, I'm not saying that at all. It's a bit more interesting than that. I don't know the answer. I've got some suspicions. But yeah, if you look in this nice simulation, it looks like the fluid flow. It looks like, well, to be specific, it looks like the smooth plains and the bursty mountains. Okay, so very kind of nothing much and then big bursts. That's what it looks like. Why is that so? Well, just think about it. I'll just look at one more thing to kind of ask, well, what does this matter, okay, that it's different? And it does, actually, because remember the nice spiky currents? The spikiness of the current is to do with how the thing is heated, and the spikiness of the current is related to the turbulence. So you go and measure this in the simulation. And the question we want to answer is, well, is the current related to the turbulence? And that's what these plots are showing. You do the nice, you know, counting of fractal patches or whatever, and ask, well, what, you know, this horrible picture is to try and show current above a certain level, and you try and draw your straight lines and things on your log-log plots, and you do conclude, well, okay, the current is doing what the turbulence is doing. So it kind of matters. It matters that this thing is you know, multifractal or whatever. It's controlling how local dissipation is happening. So that's kind of interesting. So what does, you know, so kind of just to summarise this, it's an open question. And there's several things that could be going on. Well, okay, the simulations could just be wrong. I don't mean they're wrong, I just mean they're not big enough. It's very hard to do these things. I mean, this is, you know, so much you can fit in a box. It may be that you're just not, that the data, when we looked in the data, you're just not right in the middle of the reconnection region. You're kind of more out the edge somewhere. Okay, so you're seeing a nice outflow, and so it looks like the solar wind because you just see fast plasma, and fast plasma, we know what that looks like. And so we just don't know, okay? So, and it kind of matters because if the simulations are right, it's telling you what reconnection, right being in that reconnection region ought to look like. So we could use that in the data, we could go and use it. But, you know, it also means, well, maybe you want to go and look at more on different simulations and see what's happening. Okay, so I just wanted to give you a little taste of one more thing. I've talked about turbulence in reconnection. Just a final thing, reconnection in turbulence, okay, because I've talked a lot about the solar wind. Again, just a flavour, but just to go and look at the solar wind and finally say, well, it's all a messy turbulence thing. Could that drive reconnection? Okay. So, we're doing a very simple thing now. You take some solar wind, and it's got magnetic field, and it's fluctuating around, and you just measure, make some simple measure on some specific length of the ruler, some time scale, to see what the rate of change of the field is. So I say, well, what's the field at one time compared to another time later on? So this is like looking at one eddy size, okay? And I'll just look at the rate of change of the field direction compared to the magnitude. And if you do that, you get a really bursty thing like this, okay? So sometimes the field is boring, and then sometimes you get these big bursts. And indeed, this is this kind of picture of smooth plains and bursty mountains, okay? But what we can do something else. We can bring this back to our idea of pictures. Because if you remember, as well as people like me looking from the turbulence side saying, oh, that looks bursty, there are people from the reconnection side saying, oh, I'm going to go and hunt for reconnection sites using the picture. So they have a whole bunch of times when they see reconnection. And maybe we could try and compare these things. Okay. So again, we have our picture of reconnection. Remember, this is the idea that you've got a reconnection site and you fly through it with a spacecraft. So you ought to see, you know, an exhaust coming out, and you ought to see the magnetic field reversing. And you go and you take your picture. It's a physical picture, though. There are physical constraints. And you go look in the data. And you look at lots of data and you find events, and here is one, okay? Again, this is what you see in the satellite. The velocity does something. You see little wiggles. The magnetic field changes. There it goes, changing from one direction to another. And the extra little thing, this is this PVI thing. This is this measure of how fast the field is changing. And that does a little blip in the middle. Okay. So the idea here, it's a very fairly simple one, is just to try and connect this kind of bursting measure with when you think you're seeing reconnection. So you're trying to bring two pictures together now. One is this kind of picture. This is what I think a reconnection site looks like, and I went and found it in the data. And the other is this turbulence kind of picture. This is a burstiness in the magnetic field. And are they the same, and do we see them at the same time? So we try and bring them together. Okay. So, and it's just a counting exercise. This is all this is. So you take this data and I make a threshold. And I look at what's above the threshold. What fraction of the data is above the threshold? And that's what this lambda thing, what fraction? Okay. So, you know, if we look for where in the data, we count where in the data you're greater than this threshold. First of all, what's just the percentage of data points? So that's this lambda here. So the smaller lambda, that's the smaller fraction of data points. So as the threshold goes up, I'm seeing less of the data, okay, up here. Okay, and then I ask, well, what fraction of the time there do I think I'm in a reconnection region based on what the guys did with the picture? And that's what these kinds of things, and these are current sheets as well. Okay, and then I normalize it, okay. And this is just one normalized to another, so, okay. But the basic drift, you can see these things going up quite dramatically, and this is log scale, okay. So nearly all the reconnection, the things you think are reconnection are happening when you're seeing the bursts. Lots. So this is a very, you know, fairly qualitative thing to do, just as a first step to say, well, is burstiness, in a kind of turbulent kind of way, coincident with where we think we're seeing reconnection? Because what we really want to know is how they're related. But it's kind of a first clue. Okay, and final point, of course, I keep mentioning heating. Well, is that where the heating's happening? Well, yes, it is. Okay, again, all these kinds of plots, what they are showing what the plasma temperature is doing as I go up in this threshold. So as I go to more and more bursty events, how hotter they get. So these things are doing heating for you. Okay. Okay. So I've done two things. I've talked about reconnection in turbulence, and I've talked about turbulence in reconnection. What I haven't really talked about, but I've tried to kind of allude to, is turbulent reconnection. Because that's I think Jim Dungey's exercise for the student. Okay. But basically, there are kind of two things here. We can now, using this kind of picture of turbulence, have a very good kind of yardstick for what kind of turbulence we're seeing in inertial range and in the kinetic range. So in the fluid and on smaller scales and kinetic scales. We've got a good way of going to the data and making measurements. So when you look at some data, you can say, is that actually turbulence, i.e. lots of eddies interacting, or is it just kind of some mess? Okay, so we can use these kind of ways of looking at the data, and that's kind of what I was doing with my picture of turbulence. And then, so the kind of challenging thing, and it is a challenge, is to then go and say, well, let's look in reconnection and see if we're seeing turbulence in there. Because when you look, you certainly see a mess, but are you seeing actual turbulence, or is it just a mess? And the kind of indications are, now you can see there are indications of turbulence. And there are some nice things that when you're kind of in the outflow regions, well, it really just looks like turbulence, and that's kind of nice. But when you kind of really get into the nitty-gritty, well, it looks rather interesting, and, you know, I think it's an open question. Okay. And then there's the other side of it, is just to go out and somewhere where you know you see turbulence and start looking for reconnection and asking, well, is this reconnection kind of related to the turbulence that it's in? Or does it just happen to be sitting there? I mean, this is the question. Is the turbulence driving the reconnection because it's stirring up the flow? So it's really, what I've been trying to do is to kind of show how one can start with pictures. I mean, there are numbers, obviously, but start with pictures that inform numbers, which means we can then order the data and kind of unpick some of these things, which is kind of Jim's heritage in a way. So to conclude, my general idea was that there is a power in thinking in pictures. Everything I was talking about comes from pictures. I haven't solved any equations, really. I showed you a nice simulation where somebody's tried to solve some serious equations, but everything really that I've been talking about is picture-based. But it's pictures where you build in symmetries and conservation. So both for the reconnection and the turbulence, they are these kinds of physical pictures. And so really what we're doing is using pictures to explore the consequences of physical laws, okay? The fact that you do have constraints and symmetries and so on, and physical dimension, which I didn't talk about as well, okay? And so this alters the data for us. I'm showing you data, it just looks like a mess, right? Bursty stuff, okay? But this gives you a way of actually ordering it to ask questions. And then maybe it makes new hypotheses as well. I mean, we're kind of warming up to a hypothesis here that turbulence is important in reconnection and that reconnection is important in turbulence, okay? Which is what we've been kind of saying, okay? But as I say, none of this solved the full equations, really. It was all kind of, you know, relying on the fundamental underlying physics. Because really that's kind of where we are with reconnection and certainly with turbulence, that most of our understanding is of this class. And yet that's not to criticise it, it is actually quite powerful. You can get an awful long way just with this kind of approach. That's kind of what Jim did, okay. So, I know we're going to have wine in a minute, so I'm going to stop and let people ask me questions. But as was mentioned, I do art things as well, and so I was going to just leave these up while we're asking questions. These are artworks that obey physical laws, okay? And maybe you can see some of them. This is kind of div b equals 0 going on here. So is this, but you know, this is a kind of you know, twin pendulum experiment. You know, two pendular coupling. It's also reconnection. You can see the reconnection lines. This guy, this is actually a 10-foot square painting that hangs at the physics department at Warwick that I did as part of an art project. And the astronomers might recognise this. It's like the Kobe images of the early universe. So it looks a bit like a multifractal. Okay. Although people see many different things in this, interestingly. You know, so it was quite an interesting thing in itself. Thank you.
I wonder what we'll see in it after a glass of wine. Anyway, very short time for questions.
They want their wine.
Oh no, there's
one.
There's always the hardcore here. Don't
Somebody has to do the Jim job, you know, the Jim Dungey job. You know, you can ask the hard question.
Your PVI.
Yeah.
Sorry, can we use the mic just to...
Sorry.
Your PVI
Yep.
method for determining whether you have reconnection. How do
Yeah, okay.
wait a minute. Let me ask the question. How do you distinguish reconnection from a rotational discontinuity, which is just an angular jump in the direction of the magnetic field?
Well, PVI doesn't distinguish those things. They're distinguished by other people looking at the reconnection events. So, but now PVI can't distinguish it. It just tells you about, you know, you could
claim to get very good
yeah.
agreement between your PVI and reconnection, and I'm trying to figure out.
Yeah, but you've had to be.
Out the
Yeah, but it's kind of, I know I went fast. It's to be clear about what I'm actually saying. I'm saying you take the PVI, okay, and then some other poor souls go and look and identify the reconnection events in the usual way, you know, by looking at them, and then you ask, well, do these things turn up, you know, when you see large PVI? Okay, you can never measure things like plasma velocity just from PVI, so it's a kind of statistical correlation. But yeah, what you're asking for you cannot do, and that's not what I'm saying one can do. But it's a nice kind of start to at least, you know, pick these things out.
Sandra, many years ago you gave another speech to this society where you were using sugar as a model, and it was cascading.
Yes.
Do you see, again, in these models, still a cascade happening where you get a point and then everything, sort of a turbulence starts in your models?
Well, the idea from turbulence, it's a bit okay. I mean, it's a bit tricky because when you put magnetic field in, but the fluid idea, of course, is that you drive it on the large scale, and so you produce large eddies and they break down into smaller scales. But when you start putting the magnetic field in, and particularly when you start putting the particle dynamics, I think it's rather more interesting. I mean, a possible picture in terms of kinetics is that you have you want to stir up the phase space of the particles. So if you think that you have a nice way to think, maybe you kind of have streaming particles, and they interact via a wave field, okay? That's what that pot shows, the second one along the right there. But these things interact, and they stir up, and what they do in the phase space is create smaller and smaller and smaller scales because you wind up the phase space. And there are no collisions, so well, how can you increase entropy? But if you keep winding it up, the scales become so small that eventually they do thermalize, and this is how you could get from structure and magnetic fields to heating. So it's a kind of, that's just a kind of one way one could think of this going, because it's a kind of, it is a tricky open problem that how do you heat a plasma when there are no collisions in the plasma? In the formal way, like you heat this room because the particles collide, okay? But you can't really do that, so how do you do it? And you have to create these fine scales. So it may be that in kinetic turbulence, that's kind of the job it's doing, that it's kind of doing this folding up job. So it is going sort of, it's more from large to small in that picture.
Can we thank Sandra again for the great lecture?
Thanks.